Okay, so we will finish this section, and just want to let you know, exam 2, we will do March, I believe it's like 11th, so the week after next week. Because we have a snow delay, so we are going to also delay it, okay? So let's just check the calendar. You can see here, we will do March 11th. Is that the spring break? No. The spring break is 17th to 21st, is that right? So March 11th. So we can, 27th and the 4th, we'll continue to do the exam 3 lecture material. March 6th, we have a Natty Fresher will give us a guest speaker, and 11th, we'll do the exam. Because this is give you some time to review, more time to review this section. You can go over the material, okay?
Will we get our exam ones back or no?
If you want to take, you can go to my office to take a look.
Cool.
But I usually don't return because it's an open book exam. Because if I return, then you can just do, the later students can just do it at home. You know what I'm saying? So I usually don't return, but you can take a look.
Okay.
So antibacterial mechanism, we mentioned about last lecture. Inhibition cell wall synthesis, protein synthesis, nucleic acid synthesis, metabolic pathways, and cell membrane integrity. And we mentioned that from the safety standpoint, which is we call safe for the human being or animals who are using antibiotics, then the inhibition of cell wall synthesis is the most safe one, because bacteria has cell wall. Human being and animal do not have the cell wall, only cell membrane system. So let's talk about it. This is an important slide, so we want to spend a little bit more time talking about that. Okay, inhibition of cell wall synthesis. This is coming very important antibiotics, beta-lactam. Okay, beta-lactam is a ring. It's a structure ring. I don't go chemical structure in this class because it's general education. In my major class, we talk more detail. Beta-lactam ring drug is coming from a very important common antibiotics that everybody knows is penicillin. This is the one created by Fleming back in 1930s and started to use in the medical area after 1950s. The development of the penicillin in the medical industry have a little bit of history. So we want to talk about that. Very long time ago, started to have penicillin V. Penicillin V is acid sensitive, narrow spectrum. What this means? What means acid sensitive? Which means you cannot orally take, because stomach acids will hydrolyze it. So no orally taking. What you have to do, muscle injection. Same way you do. Okay, if you have a kid, 5-year-old, have ammonia, you have to give muscle injection of penicillin V. Where you should go? Butts, is that right? Right here, I have 1 shot. That's even when I was young. When I was like 5-6 years old, I got sick, I remember that. Very hurt. Why? Muscle is in the butt area. Those are large molecular. It's very difficult to penetrate. So the penetrator have to go through all those muscle structure. And we have a joke like the kids, if they didn't very naughty, we will say, if you too naughty, we're going to give you to take a doctor and have a shots of a muscle injection with penicillin. It's like a joke. But I let you know it's hurt. But we have to do because it's acid sensitive. Okay? Then, around 30 years ago, people started developing penicillin G. This is acid resistant. However, it's still narrow spectrum. What means narrow spectrum? Which means only effective for gram-positive or gram-negative bacteria. Here, certainly, is only for gram-positive bacteria, not very effective for gram-negative bacteria. Well, I will explain to you. Then they started to happen because acid resistant. So the oral pill started to develop. Of course, it's used widely. Is that right? You don't have to do a muscle injection. You just do a prescription of the oral. Then you can take it. And what happened? Antibiotic resistant start to show up. In order to solve the problem, around 20 years ago, this guy comes out, methicillin. Okay, we use a lot in the hospital. We use too much. In some countries, even some virus caused the disease, they still use the doctors still give the prescription of antibiotics. Then what happened? Severe resistant. Remember? MRSA. What is this called? Methicillin resistant Staphylococcus aureus created nosocomial infection. Okay, then later on what we do? People have more technology developed. Therefore, amoxicillin or amoxicillin related products started to create it and become completely prescription available and orally taking, more convenient to use. So this is a development in the history about beta-lactam, about the penicillin. But there is an antibiotic resistant issue about that, yes. And what happened is, beta-lactam drugs, you can see here, they inhibit penicillin binding protein. This name is very ironic. When the people to do the research about the mechanism of beta-lactam drugs, they find these places, these protein, called the penicillin binding protein. Why? Because bacteria has penicillinase could hydrolyze these binding protein. Bacteria is smart. They have the enzyme can hydrolyze those stuff. And then in the scientific area, they named it by penicillin binding protein because when they do the research for the principles of penicillin, they find those proteins. But those are penicillinase. So bacteria can hydrolyze that. So let's talk about this, dig this one a little bit more, okay? So we mentioned about the bacterial cell wall when we talk about the gram stain. Bacterial cell wall have a major structure is peptidoglycan. And we talk about in the gram-positive bacteria, it is very thick. In the gram-negative bacteria, it is very, very thin. So this is thick, and this is thin. Now, what's the major components of peptidoglycan? We call it is composed by modified sugar, add amino acids. Okay, what are the modified sugar? NAG and NAM. So what is that? N-acetylglucosamine and N-acetylmuramic acids. You don't have to know the full name. Just the acronym is okay, NAG and NAM. So they do this alternative like arrange. Okay, then I have another line right here. I have NAG, NAM. Let's just draw a little bit more distance. So I have NAG, NAM, NAG, NAM. How do they do? They linked it together. They linked it together with what? Amino acids. There's lots of amino acids. I don't know whether you know about amino acids. I don't want to go too much chemistry. Say the C, chiral C, have H proton, amino group, carboxy group. This should write like this. Then this is all side chain, could be glycine, alanine, phenylalanine, thymine, cysteine, arginine, the 20 amino acids. Okay, so these are amino acids. And they also could cross-link like this. Like that. Okay, where is penicillin that goes? Right here. That's penicillin. So, this is a major structure of a peptidoglycan. Obviously, it is more effective for gram-positive bacteria because gram-positive bacteria have a heavy peptidoglycan and the gram-negative bacteria has very thin. Second, for penicillin, the most effective is the bacteria is growing because their synthesis, the modified sugar and amino acids. Once you synthesis, you are building it, and I'm going to break it. That's more effective. And we said about already, because we use that too much. So cause antibiotic resistant. Okay, if the antibiotic resistant happens, what we should do? We have another choice, is vancomycin. Is vancomycin. Did we mention about that? We mentioned when we talk about Clostridium difficile, and I said about a story. I said there is a 70-year-old grandma in the hospital, intensively use antibiotics, for example, penicillin for about a week, have a water diarrhea, pseudomembrane at the clitoris. So the doctor said, let's choose another antibiotics, which is vancomycin. Seems very ironic, but is that going to work? Yes, because if the bacteria is resistant for these things, for the perpendicular line, we could start to attacking here. Is that correct? These cross-linking is what vancomycin gonna work. So that's why, if antibiotic resistance happens for penicillin, we can use vancomycin because the attacking point is different. But here is the thing, lots of the time happen is multi-drug resistant. if I have a patient who is resistant to penicillin and the vancomycin, then what I do? We have another choice, is basic tracing. So what's the basic tracing? Let's say this is inside of the bacterial cell. Okay, remember bacteria have this membrane system? Fluid mosaic model, remember we talked? There is a chain here which is based by protein like a bridge. And all those chemical material has to be exported outside of the cell membrane system, go inside, then bacteria can use it to build it. And I'm going to block here. This is like during a war. I'm not going to kill the enemy. I just don't give them food. And don't give them water. They will be naturally die by themselves, theoretically. So, we can do another thing, which is I don't give you anything. I block the transportation of the nutrients. To block that, the bacteria could be killed. So this is what we have, is basic tracing. Okay, where is basic tracing? Do you remember A disk? The one component of A disk is basic tracing. Is that right? Streptococcus pyogenes is susceptible. Streptococcus agalactiae is resistant. Okay, so this is a very important slide. It tells you there is 3 different ways we could inhibit the bacterial cell wall, which is amino acid synthesis by penicillin, attacking cross-link by vancomycin, and block nutrients transportation by basic tracing. Which one is most effective? Of course, those first 2. Therefore, those are basically killing bacteria, and basic tracing is only inhibit bacterial growth. Because even you do not give them nutrients from outside, temporary, they could solve the problem by yourself. So that's something is very interesting. We talk about inhibition of cell wall synthesis. And this is important slides. We explain that to you. Okay? Okay, if a human being has antibiotic resistance of penicillin, basic tracing, and the vancomycin, all not working, what we do? Then you need to choose something which is other targets. For example, inhibition of protein synthesis. Now, by the way, what is the name of that structure in the middle? That's called a ribosome. So ribosome have 2 subunits, is 30th and 50th. So we could be attacking the large or the small subunits. So all these drugs, they have a different targets. So just want to let you know several of that. Chlorophenicol. Around 70 years ago, in 1950, chlorophenicol is using a lot because it's the most effective broad-spectrum antibiotics. Can kill both gram-positive and gram-negative bacteria very effectively. However, it does not use anymore because they have a severe side effects is attacking bone marrow system, which is the center of the immune system. So if you're using chlorophenicol, your white blood cell, red blood cell could be T cell, B cell could be dramatically decreased, which means your immune system could be damaged. So the people only using them in the life-threatening situation. Tetracycline. This is the one we don't use too often right now, only on veterinary science area. The very severe side effects is hearing loss. Streptogramins, we don't use that at all too much. because there is a severe side impacts is yellow teeth. And all the others, we use that, but only in the exception, which is the first generation of these antibiotics. Inhibition of cell wall synthesis doesn't work. Because more or less, you have some side effects will be generated. Okay, so these are the drugs for inhibition of protein synthesis. Okay, nucleic acids. What do you think of these? And I tell you one thing, once you first heard there is a drug or there is antibiotics can inhibit nucleic acid synthesis, you think it's most effective. Because everybody like a molecule. It's a very fashion stuff. However, I tell you it's least effective. Why? We're going to talk about in the exam 3 about DNA replication, transcription, translation. That's least effective. Because what you learned in your biology class is the standard procedure. In the normal life, bacteria have lots of mutation. So, if you inhibit nuclear synthesis, they're going to find a way to solve the problem. So, for example, if you target bacterial polymerase to initiate transcription, they have another way to do. You target topoisomerase, they can have a temporary, like positive supercoil to close the DNA, still there. Now, what are the use for these things? If you inhibit nucleic acid synthesis, for example, you use rifampicin. Let's say you have a RIF-resistant bacteria. What are the use? Only for lab purposes. So, for example, I'm doing a research for beef. This is a piece of beef. I want to test the antimicrobial efficacy of 5% lactic acid to kill E. coli. Let's see. Now there is a question. How do you know the E. coli is you inoculated, which means you put there, versus the E. coli is naturally existing on the surface? What's the way to do? We have to label. We give them a biological marker, so how we do? We make this E. coli resistant to rifampicin, basically resistant to 100 parts per million rifampicin. Then we inoculate it on the surface, we spread on the surface. Because we do that, we know that is the E. coli we inoculated. It's not the E. coli naturally existing on the beef surface. So if we inoculate 10 to the times of 8 cells or 5-6 logs, we know how much amount we added. That is for the lab research. So just want to let you know, inhibition nucleic acid synthesis is least effective. It's only for lab streams, because we know that's the one we inoculated, which is we call it artificially contaminants. Okay, inhibition metallic pathway. This is you should learn in your other classes. So what happened is, bacteria, they need folic acids, because folic acids cannot naturally biosynthesis by themselves. They need to take from the nutrients. But they need to synthesize folic acids. They need a precursor chemical, which is called beta-aminobenzoic acids. And I have a drug, which is called a sulfur drug, sulfolaminate. You look at the sulfolaminate, and the para-aminobenzoic acids looks very similar. What's the difference? Sulfur amino group here replaced with carboxy group. The other structure are exactly the same. You have a phenol group in the center, you have an amino group on the left. So what happens, what we're showing you here is competitive inhibition during the enzymatic process. So sulfur drugs basically is to inhibit the enzyme. So once they inhibit the enzyme, then the bacteria cannot generate folic acids. Now, by the way, you know about folic acids, which is recommended a pregnant woman to take 400 parts per million daily because they can prevent the nerve deficiency of the newborn baby. So that's inhibition of metallic pathway, but the inhibition of metallic pathway basically is only inhibit bacterial growth because it's not going to kill it. Bacteria have lots of the bypass to survive in a severe situation. Okay, that's inhibition metallic pathway. Inhibition of cell membrane integrity. Polymorphing alters membrane permeability, leakage of cellular contents. Do you know which products is inhibition of cell membrane integrity? You can get it at the countertop. Doesn't even need the prescription. If you have an itching on the skin, you can get ornament. This is ornament is antibiotics. The commercial name is ornament, the ingredients is polymyxins. That's least effective. That's why they widely used on the skin surfaces. You cannot orally take because it alters membrane permeability. Cause the leakage of the cellular contents from the inside to the outside of the cell membrane system. Okay, that's inhibition of cell membrane integrity. Very good picture right here is a conclusion of the antibacterial targets for all these listed commonly used antibiotics. So I have a question for you in the exam. What is the mechanism? You just look at the slides and you can pick from there. So that's very easy, but it gives you knowledge. Okay, what are they doing? So keep in mind, unless they are targeting for cell wall synthesis, others, they basically not very effective. Or if they are effective, they will have a very severe side impacts because human being has cell membrane, has protein, and has nucleic acids, but they do not have cell wall. So that's very interesting slides. Okay. Okay, so we finish about here. We move on to the next section. We are talking about is controlling microorganisms. So we want to talk about these things. First slides, we already mentioned when we talk about bacterial growth curve. Control microorganism has basically two levels, cidal and static. What means cidal? Killing bacteria. What means static? Inhibit. So I give you an example. If you are using 95% of alcohol spread on the surface, basically you're killing bacteria. When you buy a hot dog, you see a hot dog label have sodium diacetate, potassium lactate. Those ingredients is only static function, which is inhibit bacteria. That's why most of the food products has shelf life. You cannot be storage in your refrigerator forever. Because even those antimicrobials is only inhibit bacterial growth. Then what this means? Remember bacterial growth curve? X-axis time, y-axis is number. The growth curve. Is that right? Not correct. We're missing one here. What means inhibit? This log phase is longer. They may grow later on, but not that high. It goes here. What means killing bacteria? The curve goes here. That's a killing bacteria. That is, this is a cyto. This is static. So that's the first terminology. Cyto, killing bacteria. But here is something we want to be careful. There are lots of the products, they say germicide, bactericide, fungicide, algicide, viricide. What this means? They are basically killing vegetative cells, which means not endospores. Bacteria doesn't have endospore, which means they may not be effective for Clostridium, because Clostridium has endospore. And also I want to tell you, they may not be effective for biofilm. What this means? If you have failed daily cleaning and sanitation on the food contact surface, does not mean it will be effective. So for example, I want to clean the bench. Okay, on the kitchen, let's say. I haven't do that for a week. And today I'm gonna spray some of the antimicrobials. Does that mean it's gonna be effective? Maybe not, because if the biofilm has already been formed, it will be resistant to the antimicrobials. So be careful. This is basically means vegetative cells, which means normal bacteria. Okay, static inhibitor bacterial growth. And we could say bacteria static or fungi static, one for bacteria, one for fungi. Okay, this is something you need to know. People may not realize it. We say control of foodborne pathogen or control human pathogen. There are 3 levels. Number 1, sterilization. How do you understand sterilization? Killing anything. Killing everything. Including endospore. The second level, disinfection. Okay, what is the example for sterilization? Heating or firing or autoclave. Everything is gone. What is disinfection? Using 95% alcohol, for example. That is killing vegetative cells, not in endospore. Which means Clostridium bacillus may not be working. Did you hear about all the time the terminology called sanitizing? No, everything we do cleaning, sanitizing. What this means? This means reducing bacteria or microorganism population down to regulation. Could it be state, could it be federal register, whatever the regulation is. What this means? This means around 3 to 5 log. So I tell you a very simple example. When you buy a Clorox, especially during the COVID-19 period, you buy some sanitizer. What their label said? Effective for killing 99.9% Did you see that all the time? Doesn't mean much. What means 99.9? I have 10,000 cells. What is 99.9? I left one cell there. Is that right? I have 100,000 cells. How many cells are left? 10 cells. That could be risky if it's E. coli 0157H7. E. coli 0157H7 only need the tail cells can kill people. That's why E. coli 0157H7 is zero tolerance in beef products. So this is very tricky. That's why these products is only for food contact surfaces. You think this is huge? It's just commercialized, like advertisements. Because it's basically for me 3 log. It's not much. Just want to let you know. Sanitizing is the least level of control, which means reducing microbial population to the level they consider it safe by public health codes or regulations. Does not mean there's no bacteria there. But some of that is zero tolerance. Let's say E. coli 0157H7 in beef products. But how about poultry? We'll talk about real quick next month. In poultry products, they allow certain amount of salmonella and campylobacter to be existing. So it's very tricky. It does not mean it's zero tolerance. Okay? So just want to let you know. Now, antisepsis, which means disinfection of the tissue. Okay, this is tricky. This causes lots of problem in the industry. Microorganisms, when they're killing, after they kill, we're using general microbial testing methods to see how many bacteria are still there. But sometimes, even we testing its zero colony on the plates, does not mean they will not cause problem. Because that could be viable but non-culturable. Which means, using traditional methods, we cannot get a colony, but they still could cause a healthy problem, public health problem. So for those, we can only using molecular methods to do. There is no way to use general traditional bacterial analysis methods. Just want to let you know. Okay, this is something very tricky. So first of all, we want to explain something to you. Traditionally, to killing bacteria in the food preparation, there is a way to do, is heat. That's everybody knows. Okay, you have beef, you cook it, you heat it, bacteria will be there. Therefore, we got a curve. X-axis is time, basically seconds. Y-axis is temperature. Here, degrees Celsius. Okay. Degree Fahrenheit, minus 32, multiplied by 5, divided by 9 equals degree Celsius. Okay, just want to let you know. But the usual scientific areas, they use degrees Celsius. Here, they are actually is using a log number. So population. The curve looks like that. It's called a linear curve. Then they have a 2 index. Number 1 is called d-value. What is the d-value? Time required at a fixed temperature to kill 90% of a target bacteria in a specific food. What means 90%? That equals 1 log. Okay, what this means? 10 to the 1 equals 10, is that right? 10 to the power of 2 equals 100. Okay. Log 10, 100 equals what? 2, is that right? Log 10, 10 equals what? 1. That's a log. So 90% is 1 log, basically. Then they also have another terminology called z-value. What the z-value means is temperature required to change 90% of d-value. So z-value, which means the temperature, and d-value, which means the time, at a specific temperature. But these two pictures, which is confusing you. Why? They are doing things is in broth, in a liquid. In a real life, it's not like that. Think about if this is a steaks. This is the oven, okay? I put it there. Where do you think it will be heated first? It's on the surface, is that right? The center will be gradually heated. So what happened? The curve is not looks like this. The curve like that. Because usually the surface is more heated first, the center is later. This is called a shoulder. And lots of the time does not mean every bacteria will be killed. They could have a residue bacteria like this. This is called tail. This alone have 7 mathematics model could explain it. This is called predictive food microbiology. It's another different discipline. So these days, we talk a lot about that in the food science area because we talk about predictive modeling. The predictive modeling could use chemical signal to see the bacteria grow, relate to the machine learning, and develop a very fashion world called AI technology. Just want to let you know, thermal inactivation is not that easy. This is just an ideal linear curve. Ideally, we may have 7 different curves. Okay? So just want to let you know. This is just a theoretical status. Okay, next couple of slides is easier to understand. The conditions influencing effectiveness of the antimicrobial. Of course, the population, the large population took a longer time to kill. Okay, population composition, what it means? This means a different combination of the bacteria. So I give you a very example. If on the food contact surfaces, you have Salmonella and E. coli, it's very easy to kill. If you have a Salmonella with Pseudomonas, then it's difficult to do. Because Pseudomonas is a sporage bacteria. It's very easy to generate biofilm on the surface. If you have a combination with Salmonella and Clostridium, then it's more tough because Clostridium is an endospore-forming bacteria, which means you may need a higher temperature and extended heating time. Then what happens? The products, maybe you lose some quality, especially like a beef, because we care about juiciness, we care about the flavor, we also care about the tenderness. We don't want everything just for safety. If you're cooking a steak for 3 hours, nobody gonna eat it. It's very, very tough. So that's something you need to know. The population composition is important. Concentration, of course. Most of the time, the higher the concentration, the curing the bacteria is more effective. But maybe not linear. Duration time, usually longer exposure time, more organisms being killed, but there is a safety concern. Temperature, basically higher temperature curing more bacteria, unless heat-resistant bacteria. Or environmental bacteria, like something from the Yellowstone hot spring, that's a different story. Okay, local environments. We talk about the pH, biofilm formation, and the organic matter, especially for chlorine solution. We will mention later on. Chlorine solution is very tricky. You buy a bottle of Chlorix, does not mean you can just randomly use anywhere. You need to make sure the surface has already been cleaned. Because if the surface have dusts there, we treat those as organic matter. They will severely decrease the concentration of chlorine effectively and rapidly. That could be decreased from 50 parts per million to 0.5 in about 30 seconds. We will talk about that later on when we talk about the chlorine during the poultry meat safety section in the exam 3. Okay, physical methods of control. This is easy. Burning. So, which category is burning belonging to? Sterilization. You put a loop in the Bunsen burner back and forth, killed everything. They say water is removed, the protein, nuclear gases is destroyed. Dry heat and moist heat. This is really, I like it, to talk about the temperature. What do you think of your home freeze temperature? Your home refrigerator, usually minus 10 degrees Celsius. This is something else we could talk about. So, our food products, if it's a beef, let's say, okay, when the temperature is decreased, the water molecule